Previously, we saw how to solve the triplet paradox in the case where the travelers move at constant velocity during their entire journey, except at the turnaround where they instantly switch direction, which results in an infinite acceleration. In this second part of the tutorial, we are going to consider a realistic case where a finite acceleration is taken into account. More precisely, we are going to consider here the case where Betty and Chloe agree to accelerate with a constant proper acceleration of 10 meters per second square until they reach a maximum of 90% of the speed of light with respect to Alice, who remains on an inertial space station. Once they reach their maximum speed, they coast at constant speed for 2 years as measured by their own watches. Then they start decelerating by using the same constant proper acceleration in the opposite direction until they come to a complete stop with respect to Alice. Then they do the trip back to the station in the exact same fashion. Note that a constant proper acceleration of 10 meters per second square, which is slightly greater than 1g, is perfectly achievable with our current technology. For example, SpaceX rockets routinely have accelerations of about 3g. Also, as the rocket burns fuel, its mass decreases and it becomes easier for it to accelerate. It is therefore technically possible for an onboard computer to gradually decrease the power of the thrusters in order to maintain a constant proper acceleration. So we have three numerical values to begin with: the speed of light, the maximum speed of 90% of the speed of light, and the coasting times, which are proper times for Betty and Chloe. In order to solve the problem, we need to introduce some variables. In particular, we will use TAA to denote Betty and Chloe's acceleration time as observed by Alice. Note that we use here the Latin letter T instead of the Greek letter tau, because the acceleration time observed by Alice is not a proper time. We will denote Betty and Chloe's acceleration proper times by tau BA and tau CA. The coasting time observed by Alice is not a proper time either, and will therefore be denoted TA0. Finally, the total times for the entire journey observed by Alice, Betty, and Chloe are proper times, and will naturally be denoted tau A, tau B, and tau C. As for any physics problem, symmetries should be used in order to simplify the problem as much as possible. In particular, it is clear that the decelerating phase takes the same amount of time as the accelerating phase, no matter which triplet is observing it. Likewise, the outbound and the inbound trips take the same amount of time. Thus, we can directly conclude that for each triplet, the journey's total time is equal to 4 times the acceleration time plus 2 times the coasting time. So, in this problem, we consider a constant proper acceleration. The proper acceleration alpha of an object is the acceleration as measured in the object's rest frame. For one-dimensional motion, as in the present case, it is related to the coordinate acceleration a and the instantaneous velocity u of the object by the well-known formula a equals alpha over the cube of the instantaneous Lorentz factor. For a rigorous derivation of this formula, check out my tutorial about the twin paradox. So, the coordinate acceleration is related to the proper acceleration, but it is also equal to the time derivative of the velocity by definition. So, this leads to a differential equation that can easily be integrated by using the separation of the variables method. This leads to an algebraic equation between u, alpha, and t. This equation is easily solved for t and u, which gives the time and the velocity of the accelerated object as seen from the inertial lap frame. In addition, there exists at any time an instantaneous comoving inertial frame in which the object is momentarily at rest. The infinitesimal time during which the object is at rest in that comoving inertial frame is a proper time, d tau. Therefore, it is seen in the lap frame as dilated by the instantaneous Lorentz factor. Solving for deta and integrating over the lap frame time leads to an integral for the total proper time elapsed in the object's accelerated frame. This integral can be explicitly calculated by substituting the expression for the velocity that we just found. This way, we end up with a simple expression for the object's proper time as a function of the proper acceleration and the lap frame's time. Putting everything together, we know how long it takes in the lap frame for the object to reach a certain velocity, and we know how to relate the object's proper time to the time elapsed in the lap frame. Let us analyze now how an event is seen from an accelerated frame. So, we consider here a frame F with a constant proper acceleration alpha and some event E. Let us say that at some time t0, the spacetime coordinates of E are capital T0 and capital X0. We want to determine the spacetime coordinates of the event at some time t later or earlier. In order to do that, let us consider the accelerated frame at two consecutive instants t and t plus dt. By definition, the acceleration is the time derivative of the velocity, and this must be equal to the proper acceleration alpha over the cube of the gamma factor associated to the instantaneous velocity. But the frame f of t is at rest with respect to itself. So in f of t, the velocity is 0, so the Lorentz factor is equal to 1. This implies that the infinitesimal change in velocity of f of t after a time dt is just equal to alpha dt. And this is by definition the velocity of f of t plus dt with respect to f of t. So, let us call t of t and x of t the spacetime coordinates of the event in f of t. Now, let us call Fi1 the instantaneous comoving inertial frame of f of t. By definition, f of t is momentarily at rest with respect to this inertial frame. Thus, the spacetime coordinates of the event are the same in f of t and in Fi1. One instant dt later, in this inertial frame, the time coordinate of the event is reduced by dt, naturally. Indeed, the longer we wait, the less time there is before the event happens. The spacetime coordinate, on the other hand, is unchanged, since it is an inertial frame. Now let us call Fi2 the instantaneous comoving inertial frame of f of t plus dt. By definition, f of t plus dt is momentarily at rest with respect to this inertial frame. This implies that the velocity of Fi2 with respect to Fi1 is alpha dt. And since Fi1 and Fi2 are inertial frames, the Lorentz transformation can safely be applied in order to find the spacetime coordinate of the event in Fi2. The new time coordinate, as usual, is given by the Lorentz factor times the time coordinate t of t minus dt minus the space coordinate x of t times the velocity alpha dt over c squared. Likewise, the new space coordinate is equal to the Lorentz factor times the space coordinate x of t minus the velocity alpha dt times the time coordinate t of t. And the Lorentz factor is the one associated to the relative velocity of the new frame Fi2, hence alpha dt. But since f of t plus dt is momentarily at rest with respect to Fi2, the spacetime coordinates in it are the same. So we know now how the spacetime coordinates of the event change in the accelerated frame after an infinitesimal time dt. We can now obtain differential equations for the spacetime coordinates by performing a Taylor expansion of t plus dt, x of t plus dt, and the Lorentz factor at first order in dt. So, after substitution and expansion, we can impose the first order terms to be equal for the two time and space equations. And this leads to a system of two coupled linear differential equations. These equations can be easily decoupled by taking their time derivatives. We can then substitute this term for dx by dt and this term for dt by dt. We end up with two decoupled second-order linear differential equations, homogeneous for the time coordinate and inhomogeneous for the space coordinate. These are standard differential equations whose solutions consist of linear combination of hyperbolic cosine and hyperbolic sine with an additional constant for the space coordinate. This introduces four coefficients lambda, mu, nu, rho, which are determined by the boundary conditions. What are these conditions? Remember, we said that we call t0 and x0 the space-time coordinates at time t0. So this gives us four equations into which we can substitute the general solutions for the space-time coordinates, and then we can solve for the coefficients. Finally, we can plug the expressions for the coefficients back into the general solution, and we obtain the solution for the particular event that is considered. So, if we know the space-time coordinate of the event at time t0, then we know them at any time during the acceleration. Note that we derived this solution by assuming that the proper acceleration was to the right. If it is to the left, all we have to do is to switch the sign of alpha, and after simplification we obtain these expressions. Now, in order to avoid mistakes, it is important to interpret correctly the meaning of these equations. The times small t and small t0 represent times elapsed in the accelerated frame, while the times capital T of t and capital T0 represent the time coordinate of the event E in the corresponding comoving inertial frame. Alright, we have now everything we need in order to solve the apparent triplet paradox. So, let us start analyzing the situation from Alice's point of view. The first thing she notes is that Betty and Chloe's trips are symmetrical since they agreed to use the same proper acceleration and coasting times. So, she can focus here on Chloe's trip only. We already derived the equation that describes an accelerated object from the point of view of an inertial frame, so we can apply them here since Alice is in an inertial frame and Chloe is the accelerated object. By substituting in the equation the maximum speed of 90% of the speed of light, she finds an observed acceleration time of about 62 million seconds. She can then use this observed time and predict that the proper time elapsed for Chloe is about 40 million seconds. Alice also knows that Chloe agreed to coast for a proper time of 2 years, so she observes a dilated time of about 145 million seconds. Putting everything together, Alice concludes that she has to wait for 17 years for her siblings to come back, and finds out that Chloe and Betty aged only 9.6 years. Let us now switch to Betty's point of view. Her acceleration at the beginning of the trip is to the left, so we use the corresponding equations that we derived. We can focus on the event Betty reaches her maximum speed with respect to Alice. By definition, this event happens after her acceleration proper time has elapsed, so the time of the event is t0 equals tau BA. And when the event happens, the space-time coordinates of the event are capital T0 equals 0 and capital X0 equals 0. In other words, when the event happens, it happens now and where Betty is. By substituting these values, the equations simplify greatly, and they simplify even more when we look at the value of the space-time coordinates at time t equals 0. But at time t equals 0, Betty is still at rest with respect to Alice, so this means that these are also the space-time coordinates that Alice observes. Now we can see that there are three unknowns in these two equations, TAA, tau BA, and XAA, so we need a third equation. This equation is obtained by using the fact that, by definition, Betty's velocity with respect to Alice is the negative of the maximum speed when the event happens. By expressing this velocity as the time derivative of the space coordinate with respect to the time coordinate and using the chain rule, we obtain our third equation. For the coasting phase, the result is trivial. The time for Betty is a proper time, thus she knows that Alice observes a time dilated by the Lorentz factor. Regarding Chloe's acceleration proper time, the only information that Betty has is that Chloe uses the same proper acceleration as hers until she reaches the same maximum velocity as hers. So the conclusion is trivial. Betty and Chloe must have the same acceleration proper times. This is a point where anti-relativists claim that there is a paradox, so we are going to prove that there is none. But first, let us see what Betty's conclusion is. The formula she uses in order to determine her own proper time is different from the one that Alice used, but we can check that the two formulas give exactly the same result. Putting everything together, Betty's conclusion is exactly the same as Alice's conclusion. And since the exact same reasoning can be made by Chloe, the three triplets all agree on each other's total times. Alright, so let us look closely at the claimed paradox. The claim is that Betty sees Chloe moving, so Betty would conclude that Chloe ends up younger. But Chloe can make the exact same reasoning, so she would conclude that it is Betty who ends up younger. Moreover, Alice sees Betty and Chloe moving at the same speed at all times, so she concludes that Betty and Chloe end up with the same age, younger than her. So this is a paradox. Don't take it personally if you are discovering relativity. It is perfectly normal to be confused at first. But if you are an anti-relativist, then such a reasoning is really dumb. Oh, am I insulting you? Well, it is just a diagnostic. Anti-relativists are people who spend their entire lives criticizing relativity. You can find some examples on my website, and they have been explained numerous times for years why their reasoning is wrong, and they still refuse to understand. So yes, their reasoning is dumb. This is an obvious misuse of the loose statement according to which moving clocks run slow. The statement applies to a clock moving with respect to an inertial frame. Alice is in an inertial frame, so her conclusion is correct. But Betty and Chloe are constantly changing frames, so time dilation is not the only effect that must be taken into account. There is also a time translation that takes place. This is obvious when we look at the Lorentz transformation. We can always split the formula for the time coordinate into two parts, one that corresponds to a time dilation and one that corresponds to a time translation. And since an accelerated frame constantly changes from one inertial frame to another, these effects need to be integrated over time. It turns out that in the case of Betty and Chloe, who have opposite proper accelerations of equal magnitudes, the time translation effect cancels exactly the time dilation effect. And we are going to prove it right now. So, let us define clearly some events of interest. We will call E1 the event where Chloe reaches the maximum velocity of her outbound trip and starts coasting, E2 the one where she ends coasting and starts decelerating, and E3 the one where she arrives at the turnaround point. In addition, we are going to consider the event E4 where Betty arrives at the turnaround point. We know that in Alice's frame, the events E3 and E4 are simultaneous because of the symmetry of the problem. But since Betty and Chloe come to a complete stop with respect to her at the turnaround, Alice concludes that the two events should also be simultaneous for Betty and Chloe, since the three triplets end up in the same inertial frame. So all we have to do to prove that there is no paradox is to explicitly show that in Betty's frame, the event E3 happens exactly at the same time as her arrival at the turnaround point. So let us make a table with the spacetime coordinates of each event from Chloe's accelerated frame, and we are going to work backward from the end of her outbound trip to the beginning. By definition, E3 happens at the end of the outbound trip, thus the spacetime coordinates are 0, 0. At the end of the coasting phase, it is E2 that has 0 spacetime coordinates. Likewise, E1 has 0 space-time coordinates at the end of the acceleration. Let us calculate how these coordinates are changed at different times. We start from Chloe's accelerated frame at the end of her outbound trip during the decelerating phase. A proper acceleration during this phase is to the left, so we use the corresponding equations. Using her previously calculated proper times, she knows that the time at the end of her outbound trip is 268 million seconds. This is when event E3 happens, so we can write that when T0 is equal to this time, then capital T0 and capital X0 are 0. By substituting these values into the equations, we obtain equations that give the spacetime coordinates of E3 at any time during the decelerating phase. In particular, we obtain the spacetime coordinates at the beginning of the decelerating phase, so we can update our table with these values. During the coasting phase, Chloe is in an inertial frame, so the space coordinate of any event is constant and the time coordinate of the event decreases by the time that is elapsing. This also implies that if at time t0 the event happens at time capital T of t0, then at time t0 minus t, it will have a time coordinate equal to capital T of t0 plus t. So we can update the table with the spacetime coordinates of E2 and E3 at the end of the accelerating phase. Now we look at the accelerating phase. Chloe's proper acceleration is to the right, so we use the corresponding equations. Chloe already knows that her acceleration proper time is 44 million seconds, and she already knows the spacetime coordinates of event E1, E2, and E3 at this time. So she can plug these values for each of the events into the equations and find out what the spacetime coordinates of the events are at the beginning of the trip at time t equals 0. And we can now complete the table. Now, at time t equals 0, the three triplets are addressed with respect to each other and at the same location. This implies that the spacetime coordinates of the three events are the same for them all. So we can build a new table of events, this time for Betty, and initialize it with the spacetime coordinate of the events at time t equals 0. And now, Betty can proceed forward in time in order to see how these spacetime coordinates change. At the beginning of her trip, Betty's acceleration is to the left, so we use the corresponding equations. Betty already knows her acceleration proper time, and she knows the spacetime coordinates of the three events at time t equals 0. So she can plug these values into the equations in order to obtain the spacetime coordinates at the end of her acceleration. She obtains these values. Note that two interesting things happened here. The first one is that the time coordinate of E1 is positive. This means that in Betty's frame at the end of her own acceleration, Chloe is still accelerating. This illustrates the relativity of simultaneity. The second thing to note is that the time of E1 is greater than what it was at the beginning of the trip. This means that Betty is outrunning the event E1. In other words, if she kept accelerating, event E1 would never occur in Betty's frame, and neither would events E2 and E3. But let us keep proceeding with our analysis. During the coasting phase, Betty is in an inertial frame, so as before, the space coordinates of the events don't change, and their time coordinates decrease by the same amount of time as the time that elapses. So, we can update the table with the space-time coordinates of the events at the end of the coasting phase. We can see that the time coordinate of E1 decreased, so Betty is no longer outrunning the event. But the value is still positive, which means that E1 still hasn't occurred yet. Finally, let us analyze the decelerating phase. During this phase, Betty's proper acceleration is to the right, so we use the corresponding equation. Betty knows her own proper time, and by plugging the information about the events that she already knows at the beginning of the deceleration, she can calculate the spacetime coordinates of each event at the end of it. Let us look first at event E1. we find that the time coordinate is now negative. This means that E1, in other words, Chloe reaching the maximum velocity, happened during Betty's deceleration. We also find that the time component of E2 is negative, which means that Chloe also completed her coasting phase during Betty's deceleration. And finally, the time coordinate of E3 is exactly 0, which means that it happens now. So the event E3 and E4 are simultaneous according to Betty. In other words, Betty confirms that she arrives at the turnaround at the same time as Chloe. So we have rigorously proven that the so-called triplet paradox is a non-existing paradox. If you like this tutorial, please write a comment, and if you didn't like it because you are an anti-relativist, feel free to comment with your hatred of Einstein and his theory so that you can keep making a fool of yourself in front of the entire web.